for all of you who heard part of these topics before, I'm going to try to sort of summarize a little these results on finite element exterior calculus that has been mentioned in several talks before. And then I guess Doug in his next talk later will take this a little closer to numerical relativity. And of course this is based on joint work with Doug, with Rick Falk, who's also here, and Snorre in different ways. What I'm going to mention. Okay, so outline on my talk is that I'm going to first go back to the standard the RAM complex in 3 dimensions, talk about discretizations of that and what that lead to. Then I'm going to go a little detour to find a problem on elasticity and its finite element discretization, which was sort of a problem we worked with approximately 15 years ago, and at that time was sort of a problem that really hadn't been understood well. Then I do a little of this finite element exterior calculus, and they're going to do that via the theory of Hilbert complexes and its discretization. So some of these papers has been named or mentioned already. In addition to these papers from all 3 of us from 2006 and 2010, Doug now has his book on SIAM that just came up that might now be the best way to get into this theory. Okay, so I want to try to be very basic in case there are someone here who are not even familiar with finite element methods and weak solutions of the Laplacian. Might be too elementary, but of course what we base everything on in finite elements is that we have continuous problem where there is a weak solution. So typically, if you have a second order problem like Laplacian or maybe with some variable coefficients that we have here, the point is that you can define your weak solution. So even if it's a second order problem, the problem is sort of settled in a space where you only need to take first derivative, the Sobolev space H1. And for a nice problem like that, you then have sort of a variational principle, which also corresponds to that you're minimizing a functional. And from this point of view, if you know, a finite element method is then based on having subspaces, and it's more or less a given recipe if your continuous problem is to minimize a functional over a continuous space or space of like a Sobolev space. Then what you do discrete is you have a subspace and you minimize over that. That's sort of more or less the most natural thing to do. And for a linear problem like this gives a matrix vector type equation as once you encode your basis functions. And if you have a nice bilinear form like this, which also can be seen as an inner product, then the finite element solution is just a projection in that inner product. And therefore, in some sense, you have the optimal solution in the inner product given by your problem. And as a consequence of that, it's relatively easy to prove that it has to converge, no matter how you define your subspaces. So in some sense, the practical thing is you have to define your subspaces and you have to implement them. Okay, so here is an example, and I have to give credit to Doug, who originally did this calculation. So it's just the recipe that we just saw, but it's not a boundary value problem, it's an eigenvalue problem. The domain is something like that, where there is a hole in it. It's a 2D problem, so we discretize it with first having a mesh of simplices. And on top of that mesh, we then do either piecewise linear functions or piecewise quartic functions. And to have a piecewise a polynomial space like that to be a subspace of H1, what you need is, of course, well, you cannot just have discontinuous functions. To be a subspace of H1, you basically need continuity over the edges if we're in 2D. And therefore, the simplest elements, they give sort of degrees of freedom that generate the basis function at the corners. And when you then have two triangles, you automatically get continuity over the edge because they share 2 degrees of freedom. And if you're going to have to a quartic, it will then have be a 5 degrees of freedom on the edge. You need 5 degrees of freedom common on that edge. And that's how you build up your subspaces. And so this is then the result of this experiment. And the point is that these are done on the same mesh, but they're different spaces. But if you look at the eigenvalues, you see that at least the first one here, they seem to agree fairly enough. So they seem to give a reasonable answer. OK, so here is nearly the same problem, but it's a vector Laplacian. So we have curl, we have grad div. We calculate the eigenvalues with these boundary conditions given here. And here is a solution we will get if you use the same piecewise linear spaces, but now the vector version. So there's 2 degrees of freedom per vertex, for example, if we do P1s, piecewise linear. Actually, here's another method that I come back to. And what you at least see from these two is that the eigenvalues are rather different. So both of them cannot be correct. Well, if you look a little more and say here's a domain with a hole, well, you realize that here there will be these harmonic forms that comes in. So actually the bottom is the correct one, or more or less the correct one. This one, that's sort of then based on just the piecewise linear spaces. It just gives garbage, you can say, on this problem. So if you look at a little more, here is the 2 cases. Here is the piecewise linear one, while here is the alternative method. And you see the difference is clear. And actually, this is a correct one, and this is not a correct one. Even if we just need more or less the same as we did for Laplacian, we just take this vector valued version of it. OK, here is another example that sort of illustrates a similar effect. Here is we're solving the same vector Laplacian, but now on this non-convex domain where we have a corner. The first one here is done by piecewise linear vector valued functions. And this is done by the other method that I'm going to come back to, which is the correct one. And it's well known that solution to these problems develop singularities in corners like this. So this is, again, the correct one. The piecewise linear is not able to pick up the correct solution. So what is going on? Well, before we see what's going on, we will see in a moment that it's natural to look at these problems.
So the question, the biggest one is about the one that doesn't calculate the correct solution. Can you check error or something that tells you that it's taking the wrong result, or it's never converting?
It will never convert.
Well, it will convert to the wrong answer.
Right. No.
What happened also with four order elements and 10 order elements. The main difference is you use only finite elements as a could you force the wrong answer by saying that three residuals in some different bases or something? If you study this solution carefully, you will find out it wasn't one. By the three residuals, for example.
But this definitely illustrates why just doing this convergence test with code is not a sufficient way to operate.
Yeah. And particularly not sufficient is just to do computation that prefix or say, well, this must be the answer.
Okay? Okay. So what is, before I go to the methods, I just want to introduce now the RAM complex, because this is sort of fundamental for these problems we have looked at. And of course, just to repeat, this is a complex, because when you put two operators together, we get 0. And we call these complexes exact if exactly the kernel of the curl is exactly the gradients, and this of course has to do with the topology of the domain. And that sort of explains what we saw, that when we had a hole, that we got a 0 eigenvalue. So these are sort of the spaces that we will then encounter. So standard H1 space where functions in L2 and gradients in L2. And the same for H curl and H div. It's L2 with the operator in L2. That's sort of what sort of comes in. And what is sort of a key thing for understanding this problem is to design finite element subspaces of these spaces. So what is this method that we used for the vector Laplacian? Well, if you look at it this way, you can formulate it sort of just in an H curl version. You can have different versions, but what we did here was we introduced sigma as a new variable, as a divergence of u, and then we wrote this as a system. And the advantage of that, you can write this as a system where you just, again, have a weak formulation where you just evaluate first order differential operators. So this was sort of the approach that was used. So to use that approach, we need finite element subspaces of H1, and we need them of H curl, the space H curl. And to the space H curl now, that means when you have a face in 2 dimensions, the only thing you need to be continuous, it's a tangential component of the vector field, not everything. Okay, we just for completeness here, in relation to this the RAM sequence, we can also in the same way formulate 2 ways of getting weak solutions of the standard Laplace problem. If you just omit the coefficient like this, then the most standard way of doing a weak formulation is to integrate by parts and get gradient times gradient and get this variational form here. But we can do the same thing as we did before, introduce an auxiliary variable that in this case would be a sigma, which is a gradient of u, and then you again will get a system. And of course, in a PDE setting, these kind of model problems will be more or less indistinguishable. But when you're going to construct finite element subspaces and so on, it is a different story. And so the discretization based on the 2 formulations will have different properties. Okay, so here is sort of for all these problems, the setup is then the following. We have the continuous or Sobolev type de Rham complex, and we have to build subspaces. Okay, and to build subspaces for all these spaces, this was something that was realized in maybe the 70s and the 80s, and there were done a lot of research on how to build these spaces, and it became very well understood how you can can do it. And here are sort of the simplest spaces in 3 dimensions. So we had this 2D case over there. We use vertices. Here is the same thing in 3D. You just use vertices, and you will get the continuity you need to be a subspace of H1. Here is the simplest space to be a subspace of H curl. What you need then is tangential continuity over the surfaces. And this is, you can get a 6-dimensional space. It's basically the rigid motions you can think of locally that you build this space. The fact that you have degrees of freedom on these edges, that automatically then gives you the right continuity condition to be a subspace of H curl, because you just look at where they have common degrees of freedom, and that gives you the continuity. Another subspace, the next level would sort of be full polynomial subspaces of H curl, and where the degrees of freedom are given here. So it's 2 on the 6 edges. So this is a 12-dimensional space. So this is just 3 times a piecewise linear in 3 dimensions locally. But the degrees of freedom are not at the vertices, but at the edges, 2 for each edge, and so on. So, but the moral is that how to build subspaces of this de Rham sequence was something people knew how to do from the 80s or something like that. That was sort of a tool one had in the community. And of course, when you have these problems and that has weak solutions involving these spaces, well, you have the candidate for the spaces. And you can go up in arbitrary polynomial degree, and all these spaces are well defined, and therefore you, in theory, can get as much accuracy as you want if the solution is smooth enough. And here is the so-called periodic table of finite elements that exist, and you can find on this web page, and where it's summarized a lot, even not only for triangles and tetrahedrons, but also cubes and so on. There is a whole slew of elements that all will fit into this framework that we've seen so far. Now I want to make a little detour to another problem, and I'm going to explain why in a moment. It doesn't seem to be so much harder, but this is linear elasticity. Oh, excuse me. And so it's sort of a problem where the unknown is the stress and the displacement. And here epsilon u is my notation for what Snorre called def, which is a symmetric gradient. And we have a type of model like this where this A, which is given, is in the compliance tensor, which basically depends on these Lamé coefficients mu and lambda. And there's just one thing to note here. If this coefficient lambda, which can depend on x, if that goes to infinity, you will see here that this coefficient, with this operator A now, it takes symmetric matrices to symmetric matrices. It will sort of not be invertible in the limit as lambda goes to infinity. So that is in the incompressible case, and that sort of has some effect on the formulation of this model. So also for this problem, just not for the like for the scalar Laplacian, you can have 2 variational principle. One just based on one unknown, the displacement, and one based on the 2 unknowns, the stress and the displacement. And you see here in this formulation here, you need A inverse, so you can detect that there might be some problem as the Lamé parameter gets large as you go into the incompressible limit, because you cannot invert this thing. And that's one of the reasons why actually engineers already from the 60s, 50s and 60s, when they developed the finite element method, they really wanted to have good methods for this mixed system here based on this Hellinger-Reissner variational approach. But in the early days, they found, okay, they could do things, but they always came up with spaces that much more complicated or more complicated than they wanted it to be. They had to use higher order polynomials, or they have to do special meshes where you refined inside a tetrahedron or something like that. So it was considered a problem where they wanted really to have solutions here, but it was not so well understood why it was more difficult. Because actually this problem here is also now related to a complex, but not to the RAM complex, but what we have called the elasticity complex, and which probably has different names in various groups. So what is this elasticity complex? Well, you start with rigid motion, that is a 6-dimensional space, and from this one, the first space is vector-valued H1 functions. On that one, you take the symmetric gradient, brings you into a space of symmetric matrix fields. From this one, you can take now this second-order operator. And this is, if you have a symmetric matrix field, you basically take curl of the columns and curl of the rows. Or if we think about all operators here, that works on matrices, that they work row-wise, the T stands for transposed. So you take you take curl of it, you transpose, and you take curl of the rows once more. And this operator has the property that it takes symmetric matrix field into symmetric matrix field. And it's also easy to see if you now take the divergence of that row-wise, you end up, that is well defined, that the divergence of that, you get 0. So this is, again, a complex. And we have named it the elasticity complex. I think in our papers, I think it's also referred to as a Kroner complex somewhere. This operator that comes up here, the second order operator, Snorre was touching this one too, can be called the incompatibility operator. And of course, as Snorre pointed out, this is also can be seen as a linearization of curvature. So this is probably the nearest I would come during my talk to relativity, but I think Doug will, in his talk, try to spin a little further on this and get the connection maybe a little clearer to relativity. What you said? It is, yeah. Okay, so let's go back to this this mixed formulation that I mentioned before, based on stress and displacement. So this would be a method like this. If you're really going to carry out this method, you would sort of need a subspace of this HDiv space and a subspace of this L2 space, be finite element spaces, and you can set it up. And it looks very much like the mixed method for the scalar Laplacian, except for the scalar Laplacian, this will be a vector space. Now it's a space of symmetric matrix fields, and this would be a scalar space, and here it's a vector space. But apart from that, it looks very similar. And also, I'm going to explain the theory later. It's sort of well known what you need of these spaces. It was well known, even at the time when we started looking at it, how to get a stable method. But actually, to get stable subspaces here was hard. This was what the engineers couldn't do, or couldn't do as simple as they wanted, at least back in the 70s. And so when we started looking at this problem, that was more or less the state of the art when we looked at it 15 or 20 years ago, something like this. So it's sort of interesting to try to understand why it's hard. The only thing that seems to be different is that you have this symmetric tensor, and the continuity you need for that's going to be in HDiv of symmetric matrices is that you take the matrix and apply the normal vector at each face, and that's going to be continuous. That will be the continuity condition you get to be in that subspace. So we are in this situation. Here is the de Rham complex, right? And here is this elasticity complex. And so in like 15 years ago, it was very well known how to construct all the subspaces here. But it was not so easy to construct the subspaces here. And this seemed to be sort of a puzzle, in particular because some people could tell us that actually in some sense these are equivalent. At least in the sense that if you look at the topological information that you have in these two complexes, they are actually the same. What you see of topological properties of the domain in these two, all this information is actually the same. So when we started looking at it, our first approach was to try to understand what is going on and why is it harder. So we try to see this connection between the de Rham complex and the elasticity complex. And what you should do then is you should actually not look at just one copy of de Rham, but you look at 6 copies of it. You start with 6 copies of de Rham, naturally grouped in a product of 2 3-dimensional copies of de Rham. And the starting point is a triviality, because you just write them up and look at it as a de Rham complex with values in R3 cross R3. And of course, then that is a complex if each component is a complex. And you would have differentials now of the form d diagonal dd, where d is something you should think of as either grad, curl, or div. It's sort of a kind of obvious. Then you do sort of a twisting of the complex, which is really sort of a relative trivia. I don't want to do it in full detail, but it's sort of a mapping of the complexes, which doesn't really change anything when it comes to topological properties, for example. So this corresponds, to a mapping, and maybe, a mapping like this, and this will actually turn this complex into this guy here. So now there is a coupling between the 2 levels, right? Which you can see from the process you're doing, and you're ending up here and down here. It's still 3 components of the de Rham complex, but they are now coupled by these operators here. And these operators are actually algebraic operators. That's a simple thing you can carry out. You can see what they are. So you end up with now new coefficients of your product complex of this form. And these SIs, as I said, they are algebraic. The first one is what we at least note skew of a vector. You take a vector field and make it into a skew symmetric matrix. Up to a sign, there's sort of just one way of doing that. The second one is an operator that takes matrices to matrices, and it takes a matrix, it takes it transposed, and then it subtracts trace of it times the identity matrix. And in particular, this is an invertible matrix, and its inverse is this one. The last one now is sort of the opposite of the first one, or the dual of the first one. So this acts on matrices and gives you a vector, and we call it the vector skew of the matrix. So what you do is you take a matrix, you take its skew matrix, and you represent that as a vector by doing the opposite way of what we did up there. Okay, so here is this twisted complex again, where I just put names, at least on these two here. And now it's sort of relatively simple from this again to get the elasticity complex. What you do is you start projecting this thing into not the full product of these things, but to subspaces. So you do a projection, and the way you get this second order operator is you say the element here and the element here, they should be connected such that the curl of this one is the algebraic operator S1 of this one. And this gives you then a complex down here where this operator is nearly this curl T curl I had. Now it's curl S inverse curl. And then I have to get the elasticity complex, we have to do one more step. I have to do a projection to get symmetric matrix field instead of general matrix field. So it's sort of thing. So what was the purpose of this? Well, our purpose was that we could replace these complexes here by a lot of discrete complexes because we had all of them available. So the question of could we put them together such that we can do this process and get elements for the elasticity complex. That was sort of our approach. And of course you find out, as you often do when you do discrete things, that something works and something don't work, right? And for example, in the continuous world, or in the L2 sense at least, this operator here is invertible. But it showed that it was very hard to make these discrete spaces. We had a lot of H curl spaces. We can do them vector valued. We have a lot of H div spaces. We can do them vector valued, but such that this thing here is both onto and invertible. That was more or less hopeless. So we have to. So our approach to this was now to say, okay, we have these spaces. Can we now get something that gives a stable method? And what we found out that at the discrete level, we didn't really, for the elasticity problem, we didn't need this operator to be an isomorphism, to be invertible. We could get away that it was onto. So we have a discrete space here that should be onto the space here. That was sort of what we needed to do the things we needed for the to get stable methods. So remember, if we're going to do discretizations of this elasticity problem, we basically needed a space here and a space here. But we wanted the space here to be of symmetric matrices. That we couldn't quite do, so instead we ended up with a formulation that we call a weak symmetry, where we have a finite element space here, a finite element space here, and one here, and then we express the symmetry by saying, if I take the V skew of this one, I should get 0, or 0 in a weak way. But what was surprising then, in addition, if we want to analyze this method that then had three discrete spaces, we actually also needed 2 more spaces because we needed tools over here to be able to analyze it. And in this way, we needed a lot more insight than just the spaces that went into the method, at least the way we did it. So I'm sort of bringing this up because it shows that really to design numerical methods, you need a lot of insight sometimes in continuous problems that you're approximating, and this is particularly true if you're going to do it by finite elements. So here's a summary of what I said. This was the elasticity problem was studied already in the 60s and the 70s. They couldn't really understand why it had the complexity that it seemed to have. So we used this BGG approach and was able to come up with new methods. And with this weak symmetry, we could even do piecewise linear guys. We could come up with relatively simple elements. And one other thing that actually that comes out of this construction here is what is built into this construction is there is a commuting property going on. That if I start here, let's say I start here, if I take the skew operator and make that into a skew matrix and take curl of each row, then actually that commutes with going this way, maybe up to a sign. That is, if I first take the gradient and then take this S1 operator. So it's a lot of identities that was in there. And a lot of these identities was sort of, you know, if you're going to check them when you do vector valued functions like this, you had to do some calculation. It wasn't apparent that that was true. But when we did things in differential forms instead of doing in vector calculus, all these things came out much simpler. And that was actually one of the reasons why we started to look at finite element exterior calculus, because it sort of, this observation pushed us a little in this direction. Okay, maybe I should speed up. So this was sort of, we didn't really, so when you do finite element exterior calculus, we do not restrict ourselves just to the situation of our tree. We can do it in Rn. We can do the similar, instead of these spaces H1, H curl, H div. We can do spaces of differential forms, where instead of having curl, div, and gradients and so on, we have the exterior derivative, and defining this space, a type of Sobolev space of differential forms. It should be L2 forms where the exterior derivative is in L2. So typically this exterior derivative, of course, maps then a K form into a K plus 1 form. And sort of it's a complex, because if you put two D's together, you get 0. That's sort of the standard set of differential forms. Okay, but really to analyze this thing, to analyze everything we had before, and to analyze the setup of differential forms, really we found out that the right way to analyze the property of the numerical methods was to do an abstraction, and instead of look at these concrete cases, you're looking at a sequence of Hilbert spaces and operators that make that into a complex. So here you can think about these V spaces. They sort of are abstractions of H1, H curl, H div, if you want to think about it. But when you do this abstract, you realize that it's not enough to have, for example, H curl, H div. You also need the spaces that correspond to L2, because when we define this FEEC, these Hodge-Laplace problems that we always define, in addition to H div, we also need the L2 of vector, of the vectors. So at each level, so in some sense, the more correct way to say is our fundamental space is this space W that the V space sits inside. So H curl, H1, H div, they all sit inside the L2 space. And that the differentials are really unbounded operators defined on these spaces. And sort of the inner products that then comes up is always these W space that in the concrete setting, or at least everything I have mentioned, will be L2 spaces. And in this setting, there is the reason why then the theory is simple is that then there is not so many concepts. We have these concepts. Sorry. So really, we just have the abstract differential operators. They, of course, we should have d squared equal to 0. That means that when I take d of the previous space, I get a subspace of the kernel of the next one. And naturally, we then can sort of make a decomposition of each of these spaces. I can, of course, make a decomposition out of the kernel and the complement of the kernel, but the kernel is again can be decomposed into the range of the previous one, and what is left over is then corresponds to harmonic forms. That's sort of the abstractions of all these things. And actually, to get everything now to sort of get the theory work at the continuous level, the basic assumption is that this, the range of D is going to be closed in the next space. And when that is closed, it follows that you have sort of a suitable Poincaré inequality, which is basically what you need to get well-postness of all these mixed problems that you know can set up at the abstract level. In addition, you should have that this abstract space of harmonic forms is finite dimensional. So if you have that, then you can now set up this mixed problem again, just that we have seen a couple of times before. And you more or less, well, you can see if you formulate this problem like this, you see this problem will not in general have a unique solution, because if you throw in pairs 0 and u, where u is a harmonic form, that will satisfy this equation with f equals 0. So there is no uniqueness. And this is sort of fits with that harmonic forms that corresponds to 0 eigenvalues of your operator. So if you're going to have this problem in this way, you need to have an extra ingredient to take care of the harmonic form. So, but for the rest of the short discussion we have left, we say, let's assume that there are no harmonic forms. Then this system will have a unique solution, and it will have trivially have the right, the stability you want. And the stability constant depends only on this Poincaré constant that comes in from this boundedness of the range of the D. So that's sort of the only thing that comes in to the abstract theory. So if you have that, you know, can do approximation of such complexes. So of course, if this is now our Hilbert complexes, we can have a family of subcomplexes. That means this should be a complex by itself, and the spaces should be subspaces. And that's exactly what we know how to set up, at least for the realm complex and all these things. And we have all these spaces. And so there's one more ingredient coming in, and that is we should have projection operators going from the continuous level down to the discrete, such that these commutes, I can go this way or this way and get the same thing, and they should be bounded in the right norms. Okay, so that's the whole setup. Okay, you have, so this is, as I said before, finite elements is more or less automatic, because you just construct subspaces, and then you're going to throw in your subspaces in your weak formulation, and you have your method. So here there's one more ingredient, is these projections. Okay, but now if you have this, you can look at the discrete problem, and of course this is a problem, it's exactly as a continuous problem, and the continuous problem needed only this Poincaré constant to be well posed. So if I need something stable, that is have uniform well-postness in the discretization parameter, I need the similar constant to be bounded. Okay? And this constant says, how can I measure the L2 norm in terms of the norm of the derivative when I'm orthogonal to the kernel. And the point is now that these projections that I introduce, they are not used in the method, so why do I need them? Okay? I said I needed these projections, but they are not used in the method. But the point is, they are used in the analysis. Sorry. They are used in the analysis, and we can take this discrete Poincaré constant, and we can bound it by the continuous one and the operator norm of these projections. So in some sense, at once, you have them, you know how to, you have a stable method. And in fact, this is an if and if theorem. So in some sense, if you're going to have a stable method, they have to be there in some way. Of course, they don't have to be easy to construct, but in many examples, they can be constructed, and therefore also you have a tool for proving stability. And not only that, you also can show that in these cases, like what you want for finite element methods, that the error that you have is actually proportional to how well you can approximate in that space. And that's what you always want to have of a finite element method. You make subspaces. You can check how well can I approximate with these subspaces. And a good theory should then tell you, or a good method should have this property, that your method gives an error that is just proportional to that, maybe with some constant that come in, but then you at once have control over convergence. So in some sense, I would say these guys here is our main tool for making the connection between the continuous problems and the discrete. If you do numerical analysis, we just don't want some discrete sequence or a complex, for example, that is analog to the continuous one, but they have to be related in some way. That's convergence, right? If you go in convergence over method, and these operators, these projections here, is exactly what gives you the tool for doing that. So in this setup, in some sense, everything works, and everything is then kicked back to verifying these properties. So there's basically, you have to have this closed range of the operator, which is sort of an analysis property, and we need to construct spaces such that we have these projections that are bounded cochain projection. They give the commuting relations, and they are bounded. And then that's sort of close to an if and only if setup. So if we have that, we have what we want. Okay, so the reason why I did this first is sort of when we now go back to the Ram complex in the setting in Rn, it's sort of clear what we have to do, right? We have to construct subspaces. We should be able to identify the bounded projections, and if we do that, then all problems that can be formulated as this Hodge-type Laplace problem related to this sequence will actually converge, and as long as I can construct the spaces. So I'm going to just wrap up with just how to do this now in the setting of the Ram complex. I just do quickly. We can do subspaces of differential forms, and if we are in Rn, we have a grid of simplices, simplicial grid. We typically design our subspaces as piecewise polynomials again. So therefore, you have to start with polynomial differential forms, and a polynomial differential form of degree R that just has this property. A differential form is something you apply to k vectors, and it's a PR, it's a polynomial of degree R, that once each time you put in k vectors, you get a scalar polynomial of degree R. That's the definition. So that's the polynomials ones, and if you remember from the Ram complex, I also had something that was not full polynomials. For example, in the lowest degree, it was the built up from local rigid motions, so that's not all linear vectors. It's just a subspace of them. And the way you can define this in the general setting is to introduce this Koszul operator. So the Koszul operator, if you apply that to a polynomial form, what you do is that's going to be, if you have a k form, the Koszul of it is going to be a k minus 1. So it sort of goes the other way than the exterior derivative. And what you do, the Koszul applied to k minus 1 vector is the is the differential form itself, omega, call it here, applied to these k minus vectors and the vector x itself. So this Koszul operator, that will have this property that when I apply it, I decrease the order of the form, but I increase the polynomial degree. So it's exactly the opposite thing of what the differential would do, which will decrease the polynomial degree and increase the order of the form. So, and actually, there is a relation here then in for polynomials. If I have a polynomial k form omega, or a harmonic k form omega, and put the two together in this way, then I get back to the thing I started with. And this is sort of a relation we can use to define these spaces in between the polynomials. So what we call the PR minus spaces is everything in PR minus plus the Koszul of PR minus 1. So this will have, these guys will, at least if the harmonics one will be PR, but it would not be everything in PR. So it gives sort of the right spaces in between. So these two families of spaces is really what we build everything up on in these cases. They are more or less the only spaces that are affine invariant. If I do an affine transformation, they still are belongs to the same class. And from this one, we can now build up degrees of freedom, because that's what we have to build up of finite element spaces, like we had here, right? We have to build up locally on each simplex the degrees of freedom. And this maybe looks a little complicated, but it sort of is a nice duality here, because if I want the degrees of freedom, if I want the degrees of freedom of a polynomial form, then I have to take integrals over my faces of my or my simplex against the PR minus guys of the right order and the opposite for the other. So these are sort of a tool we have. And these degrees of freedom now will have this property. If I put this together on a grid, it works in Rn, but here is just a figure in R2. Two simplexes that share the degrees of freedom, they will then have a certain continuity property, and that's exactly the continuity property you need for them to be a subspace of H lambda k. They have the right continuity such that they are in a subspace of the space they should be. So, and when we have degrees of freedom like that, that also defines what we refer to as canonical interpolation operator. Because if I have a smooth differential form, I can just copy these degrees of freedom, and I get an element in the that describes an element in the subspace. So this defines projections, but unluckily, they are not bounded, and that's sort of easy to see. Even in 2D, if I take a function in 2D and have to take its values at points to get the interpolant, that will not be bounded, right? And not in higher dimension. I cannot take. So you have to do some mathematics to get bounded projection. You have to fix them, but this can be done in several ways. Actually, the simplest way is actually to combine these guys here with smoothing operators. And if you do that in a right way, you can get operators that have all the properties you want. They still commute, and they are bounded. Actually, you can make them bounded even in L2. But this is sort of a mathematical fix. So that's more or less the outline of this finite element exterior calculus, very short, building up this theory. And in particular, I wanted to sort of explain that for some problems, that maybe to know a little more about the problem than just seeing the differential equation and the boundary condition can give you insight to how you build a method. And that's definitely true for finite elements. If you're going to have good finite elements, the basis is to have a good weak formulation that gives you the stability properties, and you start from there. So I think I stop there, and then maybe Doug in his talk, he will go further in his way, but this will be a background to some of what he's saying.
That you showed at the beginning,
Right.
and you used the theory to debunk.
Right. I didn't talk about the theory of eigenvalue problems. So, but if you go to the references, you find eigenvalue theory. So at least explaining that the method that works. I don't think you can do it for any operator. This is more special. But I think the insight is the reason why you're starting with 6 copies. If you know you want to have the elasticity complex, you know that the kernel of the first operator is a rigid motion, which is 6-dimensional. So in some sense, this gives an indication that that's a smart way to do it. But